So let's let me introduce Kai Liu. He is a third-year student in the Blumenthal group, and he's going to present his work on ultra-low line-width lasers. Kai, please go ahead and share your screen.
Okay, thank you, Michael, for the introduction, and thank you for the opportunity for Photonic Society to give me this chance to present our recent work on Brillouin lasers. So let me share the screen. So can everybody see the slide okay?
Yeah, we can see it.
Okay, great, thanks. Well, so my talk today focuses on Brillouin laser. So this is our recent work, Milliwatt threshold, ultra narrow line with photonic integrated silicon nitride Brillouin laser. So as we all know, traditionally the resonator Q is the very crucial parameter to achieving narrow line width laser emission. This is the famous Schawlow-Townes line width equation, where there are two parts play, the upper part and the lower part. The upper part is actually the spontaneous emission rate captured by the lazy mode, and the lower part is actually the buildup of the intracavity photon number. So for example, let's take a look at two laser cavities, one with low Q, the other with higher Q. So a higher Q resonator with a narrow lasing line width will allow the lazy mode to capture way less spontaneous emission noise compared to the wide resonance resonator or lasing cavity. And on the other hand, a higher Q would allow the lazy mode to accumulate a much larger intracavity photon number. So combining these two aspects, a higher Q would definitely give you a much narrower line with laser emission. So then let's take a look at the landscape of semiconductor line width versus the lasing cavity Q. So traditionally, the monolithic DFB lasers, where the cavity is mostly made up active waveguides. The active waveguides, which provides gain, which are also very lossy. So the Qs of those cavities are on the order of 1,000 or several thousand, and the emission line width is typically on the order of megahertz. And then, scientists began to extend the lossy active waveguides with passive low-loss waveguides, such as, low-loss silicon waveguides, or even ultra-low-loss silicon nitride waveguides. So this is a recent work here done in Bauer's group by Chow. Where the extended cavity is mostly made up of this ultra low loss silicon nitride, and these extended DFB lasers can achieve line width on the order of kilohertz. And then most recently, this is a recent work also here at GCSP demonstrated by Bauer's group, where a megahertz line with DFB laser is injection locked to a ultra high Q silicon nitride resonator with Qs up to almost 200 milli. And this injection locked DFB lasers can achieve line width down to Hz level. And so as you know, the Schawlow-Townes line width rules anywhere in the spectrum. So if you have higher Q, you're able to achieve narrow line width emission. So here, this is our work at this high Q end of the spectrum, where we demonstrate a resonator with Q up to almost 400 milli, and then we pump this resonator, we optical pump this resonator for Brillouin laser emission, where we can achieve a Schawlow-Townes line with below Hz level. Well, you might ask, what's the difference between the electrical pump laser and the optical pump laser? I would say the only difference could be at this n spontaneous emission, the spontaneous emission factor. The electrical pump, this factor is typically around 1, and for the Brillouin laser, this factor is typically on the order of 10 or few hundreds. So the working principle of the Brillouin laser emission actually based on photoelastic optical mechanical interaction, where a pump photon down converts into a Stokes photon plus a phonon, and the phonon frequency in the material of the glass is usually around 11 gigahertz. And also, this process also need to satisfy or comply with momentum conservation, because the phonon momentum is actually twice of the photon momentum. So the Stokes emission is actually propagating in the opposite direction of the pump photons. And this nonlinear process happens in a resonator. So the Brillouin laser emission actually goes backwards as the pump propagates. And also we need to design the resonator so that the pump mode and the lasing mode can be separated at the acoustic frequency, which is around 11 gigahertz, to achieve the Brillouin lasing process. And then I would like to mention that there is actually a very unique line width property of Brillouin laser in favor to achieve very narrow line width emission. First of all, in our waveguide, acoustic waveguide and optical waveguide, this waveguide has no acoustic guiding, and that actually leads to that the phonon lifetime is really short, and the short phonon lifetime have two benefits. First of all, it gives a huge pump noise transfer reduction. So because of the short phonon lifetime, the Brillouin gain bandwidth is wide open, and the ratio between the gain bandwidth and the cavity, the optical resonator line width, which is around 1 megahertz, the ratio between these two squared, which is around 40,000, is the pump noise suppression ratio, pump noise transfer suppression ratio. That means if the pump laser is not too bad in terms of frequency noise and line width, the pump laser's frequency noise wouldn't transfer much into the Brillouin lasing's frequency noise. And another aspect is that the short phonon lifetime, or in other words, a weak Brillouin gain peak, actually determines the minimum Schawlow-Townes line width we can achieve in this Brillouin lasing emission. So I would like to spend an extra slide here to explain this point a little bit more. Because there is cascaded emission in Brillouin laser emission, because as you pump harder, the first order Stokes begins to dump its power into the second order and the higher order modes, and the second dumps into third order. So at some point, the S1 begins to get clamped, and there's a minimum point of its Schawlow-Townes line width, and that minimum point here, the minimum point, if you do some math on the Schawlow-Townes line width equation, you will find that the minimum Schawlow-Townes width, which is this point, is actually a function of only the cavity Brillouin gain mu here, and the Brillouin gain mu is proportional to the bulk gain times the motor overlapping factor here rho, and divided by the effective optical mode volume. So let's go back to the two benefits provided by the short phonon lifetime. So yeah, short phonon lifetime, that means a weak gain and a narrow line width, but that actually means a large threshold, because lower gain, large threshold. So in order to make that compensation, we need to make the resonator Q, or the resonator line width, as narrow as possible, so that we can have a lasing threshold that is not too high. So in a word, short-lived phonons plus long-lived photons give us a low threshold narrow line width Brillouin laser emission. Okay, well, I would actually get a little bit deeper into the property of Brillouin laser emission in terms of gain threshold and line width. So the threshold equation has two parts that are involved here: the cavity line width and the Brillouin gain. So we can actually measure the cavity line width, and then we can also measure the Brillouin lasing threshold, and then we can back calculate how much the Brillouin cavity gain is, mu here. And then using this equation we just talked about, that the minimum Schawlow-Townes line width is actually a function of only the cavity Brillouin gain, then we can kind of predict the minimum Schawlow line we can achieve, and then we can then measure it to see if our prediction is valid, or which I'll talk a little bit more in detail with measured line width and calculations and such. So as I mentioned a little bit earlier, the resonator Q is very crucial to achieve low threshold and narrow line width emission. So here we do a high aspect ratio, low confinement waveguide design, which is a very wide waveguide, a very thin waveguide, 11 micron wide and 45 nanometer thick, so that we can suffer less from the scattering loss, especially from the top surface roughness and sidewall surface roughness. And also, in addition to that, we actually additionally deposit a thin silicon nitride of only around 5 nanometer after etching, before putting upper cladding, so that with the intention that the deposited thin blanket layer could cover any additional roughness introduced by the etching process on the top surface and on the sidewall. So we fabricated two sets of resonators, first with the thin blanket layer, and the second set resonators without the thin blanket layer, and to see if this thin blanket layer here in this process in step 3 really works for us. And well, we didn't measure a significant difference in Qs and line width between these two sets of resonators, proving that this thin blanket layer is indeed at work, reducing the surface roughness scattering loss. So for more loss and Q and details of this resonator, please see our recent Nature Communications publication. And then let's hop into Brillouin laser emission. So we PDH lock the pump laser to the resonator, and then crank up the pump power, and then drop the first order Stokes Brillouin laser emission by a circulator, and then fit it into an OSA to measure its power. So we were able to measure a threshold of only 1.35 milliwatt threshold here, and we're able to see up to excuse me, 3 orders of Stokes with only on-chip power tens of milliwatts. And then let's then look at the frequency noise property in line with this Brillouin laser emission. So the way we measure the Brillouin laser emissions frequency noise is called self-homodyne frequency noise measurement. It's basically unbalanced MZI with FSR of only around 1 megahertz as an optical frequency discriminator. And then we do sampling and do triggering, and then do some conversion to measure the frequency noise of the laser. Excuse me. Well, for more frequency noise measurement, please refer to this paper. So here, the Schawlow-Townes line width is actually actually corresponds to the wide frequency noise floor of the frequency noise spectrum. Well, so first of all, we measure the Brillouin laser emissions frequency noise at different pump power, because as the Schawlow-Townes line width suggested, at different pump power with different intraphoton numbers, the line width would decrease with increasing photon number. So we did see a decrease of the wide frequency noise floor, which corresponds to the Schawlow-Townes line width, or also called short-term line width. Here it's more obvious to see the wide frequency noise floor and with the frequency offset plot in linear scale here. And the minimum point is around the clamping point here, and where we measure 0.47 hertz Schawlow-Townes line width. Well, as I mentioned a little bit earlier, that there is cascading emission, and it actually prevents the first order emission from further narrowing its line width because of the onset of S2, and because of the onset of S2, the S2 kicks back at some additional frequency noise to S1. So that's why the onset of S2 results in an increase of the Schawlow-Townes line width of the S1. So what if, somehow you can prevent you know, S2 from kicking in, and then so we can keep narrowing S1. This is actually a recent work done by Professor Kerry Vahala at Caltech, which is very interesting. They somehow prevented S2 and S3 from coming in so that the line can keep narrowing down. And they were able to achieve down to millihertz Schawlow-Townes line width, which is pretty impressive work. I would also like to, to have a comparison of different Brillouin laser platforms so that we can see if this model is really at work. So as I mentioned, if you measure the threshold and cavity line width and then calculate Brillouin gain, and then you can predict the line width. So here, this is our waveguide resonator. We measure the loss and line width, and then we predict the gain, and then we calculate the gain and predict the line width, and then we indeed measure it. So we predict a quarter hertz, and then we measured half hertz. Well, they're kind of close. There could be some inaccuracy during all kinds of measurements. And I also looked at their silica wedge resonator for Brillouin laser emission. So Q or line width, and then lasing threshold, and then calculate Brillouin gain. And this is the predicted, and this is measured. They're kind of close. So that means this model is at work because this is physics. So they both should comply with this model. Well, finally, I would like to summarize my talk by saying, so we demonstrate a 422 million intrinsic Q photonic integrated resonator, and then using this resonator, we are able to achieve a Brillouin laser emission with threshold of only 1.35 milliwatt and minimum Schawlow-Townes line width of only half hertz. And yeah, that's pretty much everything I have. And thank you everybody for your attention. And I would like to take any questions.
Thank you, Kai-Kai.
Mm-hmm.
Hey,
Kai-Kai. One initial question, if I may, would be about the number of photons in your cavity. How many, what is the actual number of photons you're able to, well, I don't know if that's really that interesting.
Oh, wow.
Yeah, let's just go with it. Number of photons you're able to couple into this cavity.
Okay, I did have a simulation, but now I don't really have a number on top of my mind. But if you can look at this, this is like 1 megahertz, and here this is about 1,000. So 1,000 and 1 megahertz is 1 gigahertz. So the line width is around 1 hertz. So this is on the order of like 10 to the 9.
Yeah. Okay.
Hey, Kai-Kai, thanks for your talk. So you mentioned that some folks at Caltech are trying to avoid the higher order Brillouin effects. I'm wondering if you guys are looking to do something similar here, and also if you can go into a little bit more detail on how they might have done that.
Oh, okay. Yes. Well, yes, we do want to do something similar, and our approach is actually different from their approach, and we could employ the similar approach. Well, first of all, their approach is actually so in their waveguide and my waveguide resonator and their silica wedge resonator, these in these resonators actually they are both multi-mode waveguide, first of all. So in my waveguide, actually, this is we have single mode operation because we only have a proper coupling for the fundamental TE mode. So we don't have good coupling for the higher order mode. So that's why we only see a single mode in our resonator. And in their resonator, they have coupling for the fundamental TM mode, and they also have not bad coupling for the TM1 mode. So the pump TM0 and then observe TM. They observe the Brillouin laser emission from TM1. So here, So this here you have TM0 and TM1, and then you know, here is your TM3, but the FSR is going to change. That's how they did it. They use different modes, because for different modes the FSR is gonna change because of different index.
Okay, thank you.
Yeah.
And I think you got a question in the chat.
Let's see. How accurate can you control the silicon nitride thickness? Well, actually, I'm not a fabrication guy. Maybe my colleague Jawi can comment on that.
Yeah, so hi, Hadaki. Do I pronounce your name right? So first question, you ask, is the fabrication done in UCSB? So if I remember correctly, the process till the etching of the silicon nitride was done at UCSB, and then we sent out to our collaborator at Honeywell for this thin layer of silicon nitride film deposition and upper cladding deposition, because they have this TEOS PECVD tool, which could give us a better loss performance. So in terms of how accurate can we control the silicon nitride thickness, for this work, I think we deposited an additional layer of 5 nanometer of silicon nitride, so we talked with the clean room guys at Honeywell back and forth. We did several test runs for the oxidation of the silicon nitride thin film, and I think I do not have a number to describe the accuracy, but I think it's pretty accurate for them to deposit this 5 nanometer of silicon nitride layer and then oxidize them, because we did the process development of it. I hope that answered the question.
At least on the order of 0.1 nanometer, we could control that. Is it LPCVD silicon?
Yes, it is. Yeah, yes, it is. It is. It is as PCVD silicon nitride.
Well, back to test question. Actually, I didn't finish. So their approach here, this is their archive paper. You know, so the pump mode is one mode, and the lazy mode is the other mode. So, and you know, there isn't cascading because the FSR of different modes are different. And I think you also asked how we're gonna achieve the suppression of the second order. So what we're gonna do, we're gonna actually split the resonance where the S2 sits. So somehow we you know, this you can add splitting by put gradients on the resonator waveguide, or you can couple another resonator with the resonator so that you can split certain resonances. So that's what we're thinking right now to achieve the similar thing, so that we can keep narrowing the Brillouin laser emission, which is very tempting to do.
Cool. Good luck. Thanks.
Thanks for your question, Ted.
So you probably have mentioned this already. I remember there's one slide showing with or without the thin layer of silicon nitride. On the cavity Q. Could you quickly go back to that?
Yep.
I'm just wondering how much of a difference would that make?
Actually, we're surprised too that it's making a pretty big difference here.
So could you explain the synonym?
Yeah. So
acronym.
So what happens here is that we thought that the etching could introduce roughness on the top surface and the side wall. So we just do another process of deposition after the etching to with the intention that this deposition could cover the roughness introduced by the etching. on the top surface on the sidewall. So why do I mention the top surface? Because according to the vendor, the bottom you know, the bottom cladding is very smooth. So we don't really think that the roughness is at the bottom. So we mainly think that the roughness from the top surface, and also from what we know, that the sidewall scattering loss is not dominant at all. What's dominant here is the top surface roughness. So that's what we did, and then we measured the loss, and here is what we measure. So we didn't really have a microscope there taking a look at how roughness is out there, you know, with the deposition, without the deposition, but we measure this loss difference.
So I'm guessing the control is the one without the deposition.
Yes, you're right.
Okay. So the LPCVD is not done in UCSB, right? You got a wafer from a vendor, I presume?
Yeah, we got a wafer from
Rock Valley.
Japanese
Yeah.
company.
Yeah, we got a nitride deposition from companies, and we do the etchings at UCSB. Yeah.
Okay, so that's a one-step etch, and
yeah.
Okay,
but we're right now trying the deuterated tools at UCSB cleanroom for both the cladding and the nitride. So yeah, hopefully we can do everything in the future just at UCSB.
It seems that you not only etch the silicon nitride, but also etch the box a little bit when.
Yeah. There is over etching.
Okay.
There is over etching. Yes.
Thank you.
Thank you for your question, Robert.
Oh, I see another question of Nealing of the nitride. I have to check, but I think it's like 1200 degrees, and for how long? I think it's like 7 hours.
7 hours, 6 hours.
Yeah, 7. I believe it's 7 hours.
Yeah.
This is a good time to ask for any last minute questions.
Yeah, but I think we got a lot of good questions.
Okay. Thanks again, Kai. It was a great talk.
Thank you, Michael.